So now we're looking at logarithmic functions, guys, specifically. Okay, not just so much as just a regular log, but actually the function itself. So we're going to be looking at the graph. Exponential and logs are inverses of each other. Okay, that's why we're able to go from one form to the other so easily. Okay, they are inverses of each other. So y equals log base a of x is the inverse of y equals a to the x. So just to refresh your memory from the very first unit, to find the inverse, you do what? You switch x and y. You solve for y. And then you don't forget about your notation, okay? So good. So those same concepts are still going to apply here when you're going from one form to the other, okay? When it asks you to find the inverse. All right, so we're going to look at an example. All right, so we're going to find the inverse of f colon x arrow 2 to the x. That notation means what? You've seen this before. What does that mean? F of x. So you have f of x equals 2 to the x. And we are trying to find the inverse of that. F of x is the same thing as what? Y. So now to find the inverse, we do step 1, which says to switch. Step 2, solve for y. Now, to get the y out of the exponent, you have to take the log of both sides. Okay? By taking the log of both sides, that allows you to bring the y that's in the exponent down to the front. So then you'll have the log x equals, oh crap, I was supposed to do this the other way. Okay, sorry. I jumped ahead. I apologize. Sorry. Alright, I do apologize. I jumped ahead to something a little further down the line.
Don't use it. Yeah.
I mean, you're going to use it later on this unit.
Yeah.
Like tomorrow.
Oh, jumped the whole day.
So,
or 2 days.
We can actually write this in logarithmic form. Okay? So we'll have a log. What's my base? 2. What's going to go right beside 2? X. And that's going to equal your exponent. And there you go. There's the inverse. But I got to make sure I do step 3. What's step 3? Put my notation. You don't have to write in the notation, the arrow notation. You can just leave it. Okay? Simple enough, yes? I apologize for that part over there. So you can go from exponential form to logarithmic form using that property. And there you go. There's the inverse of 2 to the x. Right? Now, the graph of y equals log base a of x is a reflection of the exponential function a to the x over the line y equals x. Okay, that's still the same concept from the first unit. Every inverse is a reflection of the line y equals x. The same thing applies to exponentials and logarithmic functions. Okay? And just like before, when you were looking at the graphs of any old function, you can actually find the points on the inverse by just switching your x and y. Okay? Look here, you have the point 0, 1, which is always the y-intercept of any exponential function unless it's been moved up or down. But when you flip that, that turns into what? 1, 0, a point that's on your inverse. Look at the other one. This one here, you have the point 2, 4. Okay, you plug in 2 for x, you get 4 for y. If you flip that, you get 4, 2, a point that's on your inverse. So that concept still applies there. Okay, so the concepts back from the first unit still apply to your exponentials and logarithmic functions. Switch x and y, and you'll be able to plot your points on your inverse function. Okay? And just to recap, for your exponential functions, this is from prior. For your exponential functions, there was an asymptote. What type? Type of horizontal. And so that horizontal asymptote was what? No, before you say that. What was it like? How would you label the horizontal asymptote? Y equals 0. Well, when you have the inverse, it switches. It's no longer horizontal. It's now vertical, and the equation for the vertical asymptote is x equals 0. And you can see that the curve is now getting closer to the y-axis, but never crossing or touching. Okay? What was the domain of this blue exponential function? What's the domain? What is it? Negative infinity to infinity. What was the range? Was 0 included? No. So, same concept, you switch your x and y, which means you switch your domain and range. So the domain now for your logarithmic functions is going to be what? 0 to infinity, and your range. That concept still applies here, okay? So if you ever are asked to find the domain or range of your logarithmic function, well, find the domain and range of your exponential function might be a little bit easier to do, and then just switch it. All right? So, just to recap all that, domain is all positive numbers, so 0 to infinity. This is of your basic exponential function. No transformations get involved. Your range is all real numbers. This time you do not have a y-intercept. You actually have an x-intercept that's at 1, 0. And then, of course, your transformations also apply just like how they applied with your exponential functions. Okay? Your transformations also apply. All right, so just quick review of the transformations. What does this first one mean? Huh? This one's left or right because it's on the inside with the x, okay? Which one's going to be going to the left? The positive, and the one going to the right is the negative. Don't forget, everything on the inside is the opposite. What is the one here? Up for plus, negative for down. What does the negative on the inside mean? This one's flipped over the y-axis, and then the one on the outside. Say again. Flipped over the x-axis. Okay? This is probably the only time that you'll be dealing with the negative on the inside, but that's basically telling you that this transformation's been flipped, okay? You'll never be asked to evaluate, hey, what's, whatever. What about the second to last one? Is it what? It's vertical. Vertical stretch or shrink by a factor of what? By Q, and this one is a by what? 1 over P. Very good. So those haven't changed from the first unit. They haven't changed since quadratics. They're not changing for exponentials. Okay? They still apply. So don't forget about those. Now let's take a look. Here's a graph of the exponential, just to kind of go along with it and fit in that picture. So here you go. All right. Still, x-intercept at 1, 0. Its domain 0 to infinity. Its range negative infinity to infinity. Remember, any type of transformations applied to that will affect it. Okay? So we're going to sketch this function negative 2 log of x minus 1 without a calculator. Without a calculator. Just a reminder, what transformations do you do first when you're graphing something by hand? Horizontal and vertical stretches or shrinks. And then flips before you ever go up or down, left or right. Okay? So I'll give you guys I'll start you off here. Okay? It'll be easier, okay, to get the exponential form of your log to help you with graphing the points. It's a lot easier to get the points on your exponential and then just switch them to get the points on your log. Okay? Because in all honesty, if you try to make a table with what you're working with here, you're going to end up doing that anyway to even try to evaluate. Okay? So let's go ahead and let's just write just the basic log, not with all the transformations. exponential form. What's my base here? Who remembers? It is 10. Whenever there is no base, there's actually a 10 there. It's called your natural log. It starts with C. It's your common logarithm when it has a base of 10. Okay? So if I wanted to write this in exponential form, it's going to be 10 to 10 to what? 10 to y equals x. Okay? 10 to the y equals x. I'm going to make a table. Those are going to be my points that I plot prior to doing any type of transformations, okay? But when you look at this, what do you think is going to be easier to plug in? You're going to plug in for your x, you're going to plug in for your y's? Plug in for your y's, okay? Give me some numbers. 2, 1, 0. Okay, so when I plug in 2, 10 squared is? 100, okay, definitely not graphing that. So what about 1? 10, that's doable. 1, very good, because anything to 0 power is 1. What about negative 1? It's 110, and then negative 2? 1 100, okay? And actually, these are the points of your logarithmic function, okay? Because we plugged in for y, and we got our x's. So we have 102, which I'm not plotting, 10 and 1, which I can plot, it's going to be really close to the y-axis. Don't really know where that is, but it's going to be really close. So, 10 and 1, 1, 0. But no matter what, I want to make sure that I don't what? Cross the y-axis. All right, so there's the graph of your basic log base 10 of x function. Now from there, go ahead and apply those transformations, guys. Apply those transformations. All right, so I just do this. Hey guys, look over the x-axis, and how do you know that? Because the negative's on the outside. So now, instead of this graph going up like this, it's going to be basically going this, doing this number right there, right? Okay. And then what else happened to the graph? It moved to the right one, and then it also got what? You had to multiply all of your. You had to multiply all of your y's by 2 because it was a. There's a vertical stretch by a factor of 2. So to determine this, you can definitely go through those types of transformations and then multiply your y's by 2 after you flip them, or you can multiply your y's by 2 and then flip it, either or, and then move everything to the right 1 unit. Okay? For me personally, I can't visually see this, so I'd rather work with the numbers. I mean, I have the points here, so I can apply all my transformations to those points. This negative makes all of my y's negative, right? So that basically means I have to multiply all of my y's by a negative 1 as well as a 2 to have it vertically stretched and flipped. So I really can multiply all of my 2's, all my y's by negative 2 to get the points. And then this plus 1 means what? Add 1, that minus 1 means add 1 to all your x's to move it to the right. So I can add 1 to all of my x's, and then those will be the points of my graph. Okay? I'm not going to do this one. didn't even graph to begin with. But this point is now going to be what? 11, negative 2, this point. 2, 0, because I multiply my y's by negative 2, and then I add 1 to my x's. What about this one? One fraction. 11 over 10, and then positive 2, and then this is going to be really, really like small, but this one's going to be, what's this, what's the y value? It's going to be positive 4. This is going to be 101 over 100, so it's going to be past 1. That's the main thing, it's going to be past 1. So let's plot these. I have 11, 2 up here. I have 2, 0. Oh, that's a negative 2? Oh, thank you. That's what that is. I thought it was a decimal for a second. Okay, sorry. I got 11, negative 2, which is down here. So 2, 0. 11 tenths and 2. 11 tenths is really close to 1, but it's not 1, right? So I'm going to put it really close to 1, but not touching or crossing. And then 101 over 100 is another number that's really close to 1, but not crossing or touching. So that basically lets you know that your asymptote is what? More specific. X equals 1, so I'm going to go ahead and draw that in. So that way, when we graph, I'm going to get really close, but not cross or touch. And curve. There it is. Flipped over the x-axis, stretched by 2, and over to the right one. Questions? All right. Like you guys saw before, when you have a base of 10, the inverse of that is going to be 10 to the x in that particular case. This is the law that you find in your calculator, okay? It is called your common logarithm. When there is no base written, it's automatically assumed that that's a 10, and that's what you actually are able to use your calculator, type it in, and get your answer, okay? So you literally go to your log button. Your log button is located right beside your 7 button. So that's what it looks like. You have your 7 button, logs right beside that. You hit log, it'll pop up on your calculator, you type 2, and you'll get your answer. Simple as that. Somebody who has their calculator nearby, do that real fast. And you round it to 3 significant figures, yes? Perfect. Okay? Very small number. Just think about it, you're basically saying 10 to what power is going to give you 2. It's going to have to be a number less than 1. Okay? That's another way you can kind of check to make sure. Doesn't matter what mode you're in, log works the same way. Okay? Natural logarithms are ones that have e as your base. So log base e of x is basically simplified down to be ln of x. Those are your natural logarithms. So e to the x and ln of x, they are inverses of each other. Okay? Some of you guys might remember this from the past, but they are inverses of each other. Okay? And they look very similar on the graphs as well. E to the x is the own special exponential function. That base is 2.71828 and some change, raised to the x power, and ln is the reciprocal of that, not the inverse of that. Okay? As you can see here in this picture, a few more properties to go along with logarithms and natural logarithms. They are pretty straightforward, pretty common. If you have a log base a of a to the x, like before, the a's cancel out and you're just left with x. Same thing applies when you have an exponential base and it's raised to a log with the same base, they cancel each other out. Ln of e to the x is just x, and e to the ln of x equals x. So basically ln and e, they cancel each other out when they're side by side to each other, or when ln is in the exponent of e. And log of 10 to the x is just x. and 10 to the log x is just x. Because of course, if there is no base, it's assuming it's a 10, and it basically follows the first property on this slide, where they basically cancel each other out, and you're just left with x. Alright, so let's take a look at these equations here. There's some pretty simple ones, pretty straightforward ones. You will need your calculator for this if you have it nearby. You have e to the x equals 2.3. Okay? Just like before, you can either try to write it in exponential form to solve, but you can also go to logarithmic form to solve this. Here you have e to the x equals 2.3. Is that exponential form or logarithmic form? Exponential, okay? And so to solve this, we actually need to write it in logarithmic form, okay? How do you write e to the x equals 2.3 into a logarithmic form? From that previous song. It'll be ln something. Alright? If I go back one. Okay? They're reciprocals of each other. So really, all you have to do is, it's going to be ln, that is this inverse for e, of the number that it equals. And that will be x. Then you type that into your calculator. ln is located right underneath the log button. I think diagonally from the 4 button. So you type ln. You type in 2.3. And you get an answer of what? 0.833. There you go. Over here, if we look at b, is this exponential form or logarithmic form? So let's write an exponential to help us out some. How do you think we could write this in exponential? Our base is e. What are we going to raise it to? Negative 1.5 is going to equal x. Same concept as before, so we go to e. E is located by pressing the second button and then your ln button. Okay? So if you press second, then ln, you get the e feature. Some of y'all will get like just the caret. Some of y'all actually go into the exponent. You type in negative 1.5 and you get 0.223. There you go.
Hey, Mr. Anderson.
Yeah. Exponential logarithmic form. So how do I write it in log? Because what's my base? 10. I don't have to write it. This is the thing on my calculator. I just take log 0.75. Now I'll let you guys do the last one. Is this log or exponential form? So how do we write an exponential? 10 to the 3 equals x. So what is x?